Kia ora and welcome to video 15 in this series, Agile Algebra. In this video, we're going to look at inequalities. We're going to look at a particularly simple inequality, if I'm honest, but the task here requires you to solve it using three different methods. So algebraic ingenuity, if that's a term, I've just made it up, that's going to come to the fore. Good luck in coming up with three different ways in which you can solve this problem. You can check your answer on Desmos, Wolfram Alpha, or you can just wait for my solutions after the intro music. All the best. Okay, so the purpose of this question here is to help you with different tools to be able to solve inequalities. It's not something that students do particularly well. Students are really quick to just cross-multiply these things without thinking about the sign of the denominators. So if x was bigger than 1, so let's say, 10, then the denominator here is 9 and that denominator there is 11. So cross-multiplication is okay, we don't have to worry about the sign changes. But if we pick an x value that makes one of the denominators or both of them negative, then we need to take care because we know that inequalities flip around. For example, 2 is clearly less than 5, but negative 2 is not less than negative 5. So when we're multiplying through by a negative number or dividing by a negative number, inequality flips. So you'll have that knowledge because that's kind of covered in NCA level 1. Three different methods. So a first one, which is quite tedious, is a case by case. So method 1, case by case. And we consider a number line of critical values x equals minus 2 and x equals 1. Those are the two values where the denominators change their sign. So of course minus 2 is not possible as an x value because it's going to make the equation undefined. That right-hand quantity will be divided by 0. And so same with 1. So those are holes on our number line. But then we need to choose x values in the other three sections of this line. So we could say case 1. If you can hear any background noise in this video, it's students running past on the farm doing the cross country. Case 1, x is less than minus 2. Now, if x is less than minus 2, then both of the denominators of those expressions are negative. So if we cross-multiply through, then the sign won't change. Well, it will still change twice, back to what it started with. So we solve, in this case, x plus 3 times x plus 2 is less than x plus 5 times x minus 1. And if we expand out this quadratic, x squared plus 5x plus 6 less than x squared plus 4x minus 5, do some rearranging, we've got x is less than minus 11. Now, when you solve an inequality like this using case by case, the original restriction is saying we're only considering x values here, and then the solution itself is further restricting. Okay, so if x is less than minus 2, to solve this problem it actually needs to be less than minus 11. So that there is the answer for this case. Case 2 is if we're in between minus 2 and 1. And if we choose an x value in that range, for example 0, the inequality will flip because one of the denominators is negative and the other is positive. And what we're going to be doing is solving, all the working is exactly the same, except at the last step the sign will be in the different order. So I don't need to repeat all the working. X is bigger than minus 11. So the original condition, let's change our highlighter color, is inside that range. But the solution is saying it has to be greater than minus 11. Well, like it already is. Because if you pick an x value between minus 2 and 1, of course it's already bigger than minus 11. So the solution to this is actually the original condition. Any value of x in that range solves the problem. Case 3. It's kind of a bit weird though, right? That the original condition is the answer, and actually none of the working that followed really did anything. Case 3, let's get another colour. So in this range here, we're going to go between, or x is bigger than 1. So if x is bigger than 1, both the denominators are positive. So the sign flips twice back to where it started. And then this is going to, again, lead to the same set of working. X is greater than, oopsies, it's flipped twice. So x is less than minus 11. Now, that case, that's a contradiction. Because we start off with x being bigger than 1, and then we say, well, x has to be less than minus 11. Those two things can't happen at the same time. So there is no answers to this case. Okay, what that means is that the final answer to the problem, final solution set, is x belonging to the real numbers, I'm just using some fancy notation here, such that x is less than minus 11, or x is, oopsies, or x is between minus 2 and 1. Squiggly brackets around that for a set of numbers. You might also use a U for the union symbol for OR. Okay, so that's case by case. Now, case by case works fairly well for simple problems, but when the problems get a bit more complicated, it's a bit tedious. Okay, method 2. Method 2 for this. What I would think about doing is move everything to one side of the equation by subtracting the right-hand side fraction off the left-hand side. And then we don't have to worry about multiplying it or doing any cross multiplication, because we're just going to put these fractions together and say, when is the fraction negative? So if I put these fractions together, and then simplify the top stuff. So we've got x squared plus 6x plus, I keep doing 6x there. 3 plus 2 is clearly not 6. 5x plus 6, take away x squared, take away 4x plus 5. And simplify those. We've got x plus 11, all divided by x minus 1 and x plus 2. Now we do the same thing, we make a number line, and we say, what values of x does this expression on the left change its behaviour? Well, remember that, when does it go from negative to positive? When is it 0? When is it undefined? So we have the same numbers as before. We have minus 11 is a special value, minus 2, and then also 1. These values here, minus 2 and 1, are not defined for the same reason as earlier. Minus 11 is okay because the expression is defined, but it equals 0, and we want it to be less than 0. So that's also a whole. And then the final solution, we consider values of x in the 4 regions on the number line. So if our x value is really large, so greater than 1, and just think of a number in this section here, I don't know, 10. If you put 10 into that left-hand side fraction, you're going to get 21 over a positive number. You're going to get positive over positive, which is negative, is not negative. So that there is not a solution. So any x value bigger than 1 doesn't work. If you make x a really, really negative number, so like negative 1,000,000, then the numerator of the fraction is going to be negative. The denominator is going to be positive, because that's an upside, this bit here is an upside down, it's not, it's a normal upright parabola, but it's on the denominator, and it's got roots of negative 2 and 1. So if x is less than minus 2, then the denominator is positive. If x is less than minus 11, the numerator is negative and the denominator will be positive, so that means that works. Pick an x value between minus 11 and minus 2. Well, that means that the denominator becomes negative. And the numerator apologies, the denominator is still positive, but the numerator becomes positive, so positive over positive doesn't work. And then between minus 2 and 1, that's when the denominator becomes negative, and the numerator in that instance is positive. Positive over negative is negative, so that's a solution. So our final answer to the problem is x is less than minus 11 or between negative 2 and 1, which is what we got before. Okay, third possible method that I've thought about. I wonder if any of you have come up with a third one here. The third one is to think about what happens when you cross multiply. Cross multiplication works, but only if the quantities you're multiplying through by are positive, otherwise the sign changes. So how about when we have these fractions here, we multiply both sides of the equation by a positive quantity. So what we do, so I'll change my colour here, if we multiply through by x plus 2 all squared and also by x minus 1 all squared, what I'm doing is timesing by a perfect square on both sides, so the sign won't change. Okay, when I do that, the left-hand side, of course, loses an x minus 1 there and there, and the right-hand side loses an x plus 2 there and there, and we end up with x plus 2 all squared, x minus 1, x plus 3, less than x plus 5, x plus 2, x minus 1 all squared. Now this is going to require a little bit of expansion. What we can't do is cancel off x minus 1s, because we're going to have the same issue as before. If I was to go cross that off and cross that off, I'm dividing both sides by x minus 1. And dividing by x minus 1 is going to flip the inequality depending on what x is. So we don't cancel off both sides of an equation like that. We can expand it though. So I can go x squared plus 4x plus 4 multiplied by x squared plus 2x minus 3. This one x squared plus 7x plus 10. This one x squared minus 2x plus 1. Now, of course, this method is more tedious, but the general understanding of doing this stuff and how the sign doesn't change if you multiply by a perfect square on both sides is actually quite a useful thing to learn. Here, of course, it's more tedious because there's a lot more algebra. So we've got x to the 4 plus 2x cubed minus 3x squared plus 4x cubed plus 8x squared minus 12x plus 4x squared plus 8x minus 12. That's the left-hand side. Less than x to the 4 minus 2x cubed plus x squared plus 7x cubed minus 14x squared plus 7x. Something I wish I'd prepared earlier. Plus 10 squared minus 20x plus 10. Hopefully I've done all that right. And then we play the cancellation game because we're subtracting off both sides of the equation now. And subtraction doesn't change the order of the inequality. How many x cubes have I got? I've got 2, 4 is 6, and then on the other side I've got minus 2 and 7. So I've got 5 on the right hand side. I'm going to take it off the left hand side one and just be left with x cubed. X squared minus 3 plus 8 is 5 plus 4 is 9. Take away 1 is 8. Add 14 is 22. Take away 10 is 12. Linear terms, minus 12 plus 8 is minus 4. Minus 7 off is minus 11. Plus 20 is 9. And then the constant term, minus 12 minus another 10 minus 22 less than 0. And now we need to factorise this cubic. Turns out that the solutions are the same value, or the roots are the same values of x that were critical in the last one. So if we look at where have I gone? If we look at that number line there, minus 11 minus 2 and 1 with the special values here. And they're going to be the roots of this cubic, x plus 11, x plus 2, and x minus 1. Okay, and you can verify that that actually works. I can do a quick check on the sum of the roots. The roots add to minus 12. Minus 11, minus 2, plus 1 is minus 12, and the product of the roots is equal to 22, and the minus 22 constant term there verifies that. So that looks good, but you can expand it to check if you want. And then we need to consider what this graph looks like. Rather than considering what a parabola looks like here, we've got a cubic. We've got roots of minus 11, minus 2, and 1. It's a positive cubic. This term here is positive, meaning that it goes up before it goes down. So if we've got a cubic it comes through this way, and then it goes down, and then it goes back up. And we're looking for where this cubic is negative. Well, it's negative here, and it's also negative there, and they are the same ranges of x that we had in our last two methods. Okay, this method was way more tedious than the second one, and also more tedious than the case-by-case, but it's a different way of approaching it. Maybe if you found an alternative method, comment below and let us know how you did it. Thanks for watching.